Okay, now we're starting on our next chapter 19. I've actually, as you can tell, I've set up a new format here. So, chapter 19, AC circuit analysis, parallel circuits. So, let's do an introduction here, take a few minutes to get this chapter going. AC analysis, parallel circuits. Last time we did series circuits. So, we're going to go back and look through everything as it relates to parallel circuits this time. And doing the analysis, looking at the parameters, the equivalent circuits and phasors, something called transforms, and problem solving. The chapter objectives, much like we saw in the last chapter, doing the analysis of RC and RL parallel circuits this time, find the equivalent impedance of impedances in parallel, convert from parallel to equivalent circuits, and then reduce the complex circuits to equivalent series circuits or parallel circuits. So again, if we take a look at the vector relationships, we should be getting pretty used to looking at these and making a determination of what each of these vectors are telling us, if they're on the j-axis, if they're on the real axis, and the resultant or hypotenuse formed by the right triangle or the phasor relationship. So in a series circuit, we use, again, current as the reference. In an RC circuit, the current leads, so the voltage across the capacitor and the reactance for the capacitance that are plotted along the negative y or the negative j axis. E or z, the impedance, then becomes, as we said, the hypotenuse, and the angle theta then forms the phase angle between them. So for a capacitive circuit, capacitance in AC circuits cause the current to lead the applied voltage. So again, if we look at the diagrams here, we can see that in what's going on here. If we take a look at the representation of the vectors in B, we've got the voltage here on the hypotenuse that is lagging the voltage across the resistor, or the current, again, by the phase angle. And as we rotate this counterclockwise, you can see I, or V sub r, leads by that phase angle. So in a parallel circuit, we use E then, the voltage, as the reference. In an RC circuit, current leads, so I sub C and V sub C, the susceptance in this case, are plotted along the positive y-axis. So you notice when we're doing capacitance, we were on the negative. Now we're on the positive j-axis here when we're looking at it. So these are clues. These are subtle clues for you to look at and to determine very quickly whether or not you have a capacitive or an inductive, or a more capacitive or more inductive circuit. And we're going to learn more about that as we move along here. So taking an example here, if we look at what's given, we have I sub r, 7 milliamps, I sub c, 10 milliamps, and the total current and theta is what they want us to find. So very quickly, we can then look at expressing the total current in both rectangular and polar forms. So if we take what's given, 7 milliamps, 10 milliamps, plug it into the rectangular format, this is our rectangular representation using the J operator. Then using the sides of the triangles opposite and adjacent, then using the current values, we can solve for the tangent, taking the inverse tangent to give us that phase angle of 55 degrees. Switching then to the cosine function, adjacent over hypotenuse, using the current through the resistor and the total current, then we can solve for our terms that lead us to the polar representation and the rectangular representation that we have already seen. Changing the values here, I sub t equaling 300 microamps, I sub c equal to 100 microamps, then that we're going to find the current through the resistor and the phase angle. In every case here, you're going to see they're going to ask you to solve for the rectangular and the polar forms. So sine theta, IC over IT, we get 0.333. Taking the inverse, we get 19.5 degrees. Okay, using our form cosine theta, IR over IT, we manipulate it so we can solve for the current across the resistor. We end up with 283 microamps of current. Placing then our values in the rectangular form, 283 microamps plus J, 100 microamps. Notice we have a plus here now, so that's telling us that what we have is a more inductive circuit. Converting that to the polar forms, we have 300 at an angle of 19.5 microamps. So that's our introduction. When we come back, we'll take a look at RC circuit analysis using circuit parameters and variations of what we've already learned for X sub C and X sub L.